Hello students, great to see you again. Today we're going to talk more about this awesome thing called the periodic table. So we've learned a lot more and we've now know more about atoms and electrons, and so some of the things on this table might make more sense to you. I want you to also concentrate a little bit and start to pick up the naming conventions that we use. We're going to study all the rules. You don't really need to memorize them all yet at this point. If you become a chemist, you will. But I want you to start to recognize, oh, that's why we call that thing, this thing, that thing, or whatever, or where these names come from. Because those naming conventions often indicate something about where they were on the periodic table or how they're put together. All right? So that's what we're going to study today. And really, I'm going to do a lot of just showing you on the actual periodic table what some of these trends are in different things that are similar. Okay, let's take a look. First, in the first column of the table, or the first column on the left, we have these things which you probably know are called the alkali metals. Alkali metals are very reactive. As you know, if you are paying attention, hydrogen has one electron in its outer valence. Sorry, I'm going to have to actually get a different pen to show that. So there's like one electron, but even the other ones in their outer valence shell, they only have one electron, and that one electron makes them super reactive. So things in this alkali metal group are soft. They react really strongly, and especially in water. They can be totally explosive. Now, on the other side of the table, we have these things called the halogen group. These are also very reactive, but in a different way. The halogens have 7 electrons in their outer valence shell, and so they'd really like one more, and so they want to really react with things. In the middle of the table, we have this whole big group of things that we just call the metals. These are just kind of generic metals. And you'll notice a whole lot of things here that you recognize, like silver or gold or iron. I guess I should circle some of these things, but you'll recognize things that you think of classically as metals. They are conductive of electricity, they conduct heat well, they are malleable, you can change their shape, and they're generally all just kind of grayish. So they're pretty similar, and we don't differentiate a whole lot about them in the table itself, so they kind of make one big group. Now we have this group over here, which are also metals. So these were alkali metals in the first column. The second metal we call alkaline earth metals. And they are not quite as reactive as that first one, but they're also a reactive column. And then over here, we have this whole group that are kind of in the transition. So we call these transition metals. They're very ductile, the ones across the middle. Some of these act more like this, and some of these act more like this, but they're generally ductile, they're pale, and they form compounds really well. So these ones would like to combine with these ones over here to form compound molecules. Then we have this really beautiful group here. I'm going to make this one green. This is the noble gases. These ones have that perfect, lovely, what atoms like to have, which is 8 electrons in their valence shell. These ones, even though a whole lot of the rest of these elements would be solid at room temperature, the gases remain gaseous, which is why we call them noble gases. And they also really non-reactive. So if you want something to stay the same, you might put it in a container full of noble gas, so it just wouldn't react with anything and nothing would happen. And so you can tell from all of this that we have these trends on the periodic table about how things are and how things react. Now down here at the bottom, you might have noticed I hadn't talked about these ones yet. Oh, whoops, I just erased lines I didn't mean to erase, but oh well. So these ones down here, these ones get pretty crazy. They're getting huge, and so they start to behave differently. And you might notice that uranium's down here. We have a whole lot of radioactive elements down here that are so unstable that they're trying to give off or take up things, and that radioactivity means they're breaking up and not staying how they normally might be. All right, I'm going to erase all of this. That gives you just a little bit about some of the basic groups on this periodic table, but what about other trends? Well, we can find out other things. From where an element is on the table, we might be able to predict some other things about how it might behave. For example, how big is an atom? Well, I'm going to draw lines on this table based on which things are bigger and which things are smaller. So do you think the ones on the right are going to be bigger or the ones on the left are going to be bigger? Well, it turns out as we go right to left, they tend to get bigger. This is the bigger direction. And the reason that is because as you add more electrons to that outer valence shell, they actually have a more force between those electrons and the nucleus, and it pulls that outer valence shell smaller. So as we go to the right in the table, it actually gets smaller. And as we go to the left, and there are less electrons in the outer valence, they get bigger. But as we add an extra valence shell on the outside, they're going to get bigger. So as we go top to bottom, they will get bigger. So if we're looking at size, top to bottom is bigger and right to left gets bigger. What about, we'll call this ionization energy. And you don't really probably know too much what that is yet, but ionization energy means how much energy it takes to make an ion of it. In other words, if you're going to rip an electron off, how much energy does it take to do that? So you might have a sense. I mean, think about it. Which do you think would have higher ionization energy and which would have lower? So these elements over here, they only have that one electron and they're pretty happy to give it up. So they have low ionization energy compared to the ones over here. So we're going to say ionization energy is a big arrow to the right for higher ionization energy. And also, as we add more electrons on the outside, they're not as tightly bonded. So the ones at the top are going to have higher electron energy, ionization energy than the ones at the bottom. So we're going to draw a big arrow up for ionization energy. So we can see trends in the table that way as well. There's a related thing called electronegativity, and that's how tightly one atom bonds to another when we form a compound out of them. And interestingly enough, the electronegativity is the same. It is just like this energy. We're going to get greater electronegativity to the right of the table and greater electronegativity up towards the top of the table. In other words, they're going to bond more tightly to each other. And that somewhat makes sense if you think about it. So what's another trend we can look at on the table? Well, how about just plain old reactivity? We talked a little bit about that before. Can I draw an arrow from right to left or left to right for reactivity? Well, it turns out not really. These ones in the middle are less reactive, and these ones on the edges are more reactive, except for the noble gases, right? So we can kind of draw an arrow. If we wanted to color code this, you might have to do it more complicated, maybe shading, but we can say this is getting more reactive this way from the middle and more reactive this way from the middle, all except for this column, which is completely non-reactive in that way. So what I want you to understand from this is that the table itself gives us trends. And that means if you're wondering about a certain element, what about this one? What do I know about gallium? Well, you can kind of guess some things about gallium because of what you know about the rest of the trends of other things on the table. So the knowledge of the table will give you a whole lot of knowledge about what is going on with a particular element. What about that naming convention I talked about? What if I stick a couple of these together? For example, a really common element that you know about is, or not element, excuse me, compound that you know of is salt. How about table salt? Well, table salt we call sodium chloride. So we've got sodium over here and chlorine over here. I probably should have erased, but hopefully you can see those. Sodium and chlorine. So if I put sodium and chlorine together, I call it sodium chloride. Basically, if you join a metal with a nonmetal, we're going to add the IDE ending to the end of the nonmetal. So we'll say sodium chloride. What about, say, carbon dioxide? There's carbon, there's oxygen. Why do we say carbon dioxide? Well, when we write the symbol of this, that's one carbon atom and two oxygen atoms, which you'll learn more about how to write. And so the di means two. So we say carbon dioxide as in two oxygens, one carbon. But we also know carbon monoxide has only one oxygen, so we say CO. And you can read about all these rules in this week's lesson, and you'll learn more about our naming conventions for how we say the names of the different chemicals. Hope you have a great time this week.